we finished lecture 1. The chapter is about transient vibration, and we talked about impulse and the definition of impulsive force and what impulsive force will do on the changes on the status of the system. So if the system is at rest and excited by impulse, it's going to change suddenly the velocity of the mass from 0 to an n0 value equal to f hat over m, and we said that f hat is equal to the impulse, which is Newton second. Okay, and then we wrote the response as x equal to f hat times h of t, and h of t depends on the type of the system. So here we have for zeta equal to 0, that is h of t, and we have h of t for zeta less than 1 is this equation. Okay, and then you can generate for zeta greater than 1 and zeta equal to 1. So h of t is the unit, is the impulse, is the response due to a unit impulse. It depends on the value of zeta. So far we only discussed 2 types, but you can generate or obtain the h function for overdamped and critically damped. And then we solved this example, which is a spring mass damper system. It's structure, but you can model it as spring damper system excited by impulse. And we find that zeta is less than 1, so this is underdamped. Okay, and the response will be f hat times h of t, which is this equation. The impulse started at t equal to 0. It's given in the problem. So as a sketch of this is the due to this impulse is going to oscillate. This is underdamped. It's going to oscillate this way. Okay, starting at 0. So x, I will write it this way: x equal to f hat h of t, and we write it h of t because the impulse started at 0. But if the impulse, if I add on this example, if the impulse started not at 0 or applied at t equal to a is in second, then the response, if the system is already at rest, then the response will be same as this one, but it will not start at t equal to 0. So x is going to be f hat times h of t minus a, and the meaning of ht minus a, it means that h of t minus a equal to h of t. It is equal to h t minus a. You substitute for t equal to t minus a for t greater than a. Okay, and 0 otherwise. Okay, so you can put this in the second condition. Equal to 0 for t less than or equal to a, and equal to h of t for t greater than a. And if a is not 0, the response will have, you can get the same response as shown above, but it will be starting from t equal to a. It's going to be 0, and then it will start to oscillate, same as above. Okay, but its starting time is at a. Okay, this is the reason why we write x equal to f hat times h of t minus or h of t. And whenever this impulse started at a different time other than t equal to 0, you will use h of t minus a using this piecewise continuous. Okay, so this is h of t minus a. So wherever there is t in h, you replace it with t minus a. Okay, so this I will move to lecture 2. Okay, so as I said, that impulse is applied at a sharpie at a given time. You say t equal to 0 or at t equal to a. And that the duration of the impulse is approaching 0. So that is something ideal. But practically, when a force is applied or an impact using a hammer, for example, then this will take contact time. It will be short, but it is not 0. And in this section is considering the duration of the impact or the impulse. And this is called, the section name is arbitrary excitation, which means generally any type of excitation. Okay, so this is the figure shown here is the force versus time. Okay, and as you can see, this is not periodic. It is starting from 0 to t final. Okay, and this is the final of the pulse. P may be for pulse. Okay, in order to find a solution for this, you consider impulse. You consider that the given force here is made of series of impulses. And then you can use the principle of superposition. The system we have is linear, as you know, consists of inertia, damper force, which is linear, c times x dot, and spring force, which is k times x. For linear system, you can apply the principle of superposition, which means that you assume that this given force is made of series of impulses, and the response due to a given impulse is known now. It is f hat times h of t minus a. Now he didn't say a, he's using Greek letters eta. I will use this as eta. Okay, so this is the duration is delta eta that goes to 0, and this is make it as an impulse, and eta is the time at which the impulse is considered. So you find the solution due to this impulse 1, okay, which is applied at t equal to eta. So the response due to this impulse is going to be f hat at value of eta, of course, because this f hat varies and depends on the value of eta. So it is somewhere here, it is different than if it is here. So it should be f hat of eta, the impulse at time t equal to eta, multiplied by h of t minus eta. That will give you the response due to this impulse. Okay, and as you can see in the second figure, this is the impulse at t equal to eta. So this is eta. Okay, and this is the resulting response. As you can see, this response is 0 before the impulse started, and then impulse is not 0, it is responding after the impulse. There is no response before the impulse due to the considered impulse. Okay, so this is, let's say you can call this is number 1 or number 10. Okay, let's take this is number 10 and you have 9 before. And then the total solution will be the summation. Okay, so this is I, and then the total answer the total response using the principle of superposition will be summation of xi from 1 to n. Okay, so suppose you divide this into 100 impulses, then you will have a summation from 1 to n. Okay, so definition of the impulse, as we said, is the integral of f dt, and for a rectangular approximated as a rectangular area, then it is f of eta times delta eta. So this is the impulse here. Okay, it is a rectangular shape, which is same as the previous section. So f hat is obtained as the integral of f dt, but since it is also equal to the area under the curve, and since this is the rectangular area, it is the width times the height. Okay, the width is delta t, delta eta, and the height is f of eta. So that is the impulse. And the response, this is x, due to this impulse at t equal to eta, is f of eta, h of times delta eta, which is f hat, times h of t minus eta. Okay, so it as it's mentioned here, this impulse contribution to the response at time t is dependent upon the elapsed time t minus eta, and it is equal to f of eta delta eta h of t minus eta, and h of t minus eta is the response to a unit impulse started at t equal to eta. Okay, because the system we are considering is linear, the principle of superposition holds. And when you take the summation to be very large, you can replace the summation with the integration. So the total response becomes x of t integration from 0 to t of f of eta h of t minus eta d eta becomes integration. Okay, this integral is going to find you the response up to t. Okay, you can put t equal to 1 second, 2 seconds, and so on, and obtain the total solution. So the part of the, if you want to find the response up to, let's say, this point, then this part of the impulse or the pulse or the force is not affecting the response before that time. Okay, let's say this is t equal to let's say 2 seconds. So this part of the force is not affecting the response before t equal to 2 seconds. And this is the why we have integration from 0 to t. So it depends on what is the value of t. If you want to find t in general, you can make it just function of t, and then you can substitute for whatever value of t you want to find the response at. This is the integral that will give you the total response, and this is called convolution integral, or sometimes referred to as the superposition integral. So let me just write it: x of t equal to integration from 0 to t of f of eta h of t minus eta d eta. This is the integral, and this will give you the response as well. That is the solution of the differential equation. So if you have a differential equation, then f of eta, for example, let me give you mx double dot. Let me just put values. 2 plus say 50 x dot plus 5000 x equal to e to power minus t. So as you can see that e minus t is f of t. This is the force. But when you substitute in the integral, you will put integration from 0 to t, and f of eta is e to power minus eta. So you replace t in the convolution integral, you will replace t with eta. So it is e to power minus eta. So in order to proceed, you need to find how much is zeta for this problem. Okay, so zeta is 2 zeta omega n equal to 50 over 2, which is 25. Omega n is square root of 5,000 over 2. So this will be 25 over 2 square root of 5,000 over 2, which will be, I think, less than. Okay, let me just work it out. Divided by 2, and that's 50 multiplied by 2. This is 100. This is 0.25. Which is less than 1. Then you can use the h of t minus eta of the underdamped. Okay, so h of t here, we know that h of t for underdamped is equal to 1 over m. You can refer to previous lecture, e to power minus zeta omega nt sine omega dt. Okay, so in the convolution integral, we will put 1 over m omega d e to power minus zeta omega n. Instead of t, you put t minus eta sine omega d. Instead of t, you will put t minus eta d eta, and you integrate over eta. That will be the response. Okay, so let's see the example we have here. Okay, determine the response of a single degree of freedom system to the step excitation shown below. This example has two parts. Okay, for zeta equal to 0 and zeta less than 1, underdamped and undamped. Okay, the response or the force is called step excitation. As you can see, it is 0 before t equal to 0 and suddenly equal to F naught. That's called the step. Okay, and for underdamped, for undamped, h of t is 1 over m omega n sine omega nt. You can refer to lecture 1. Okay, the response of the undamped system becomes, as usual, you will write x equal to integral of f of eta h of t minus eta d eta. And then you will substitute. F of eta, we have f of t is constant. It's equal to f naught. Okay, so f of eta is f naught. Okay, so let me do it on this side. Okay, so x is equal to integration of f of eta h of t minus eta d eta equal to integration from 0 to t. And f of eta is f naught. And h of t for undamped is 1 over m omega n sine omega nt. And since here we have t minus eta, we replace t with t minus eta d eta. And then you can take the in the constant or any term that is not function of eta outside the integration. You are integrating over eta not over t. So f naught over m omega n outside the integration of sine of omega n t minus eta d eta from 0 to t. Okay, integration over eta, not over time. So this is f naught over m omega n. Integration of sine is minus cosine, but since there is a minus in front of t of eta, this becomes plus. So it is cosine omega n t minus eta divided by omega n from 0 to t. Okay, so this is f naught over, you take omega n there, this becomes m omega n squared. When eta equal to t, this will be cosine 0, and cosine 0 is 1. Okay, you don't, I will do it step by step. Cosine omega n t minus t, which is cosine 0, minus cosine omega n t minus 0, because I'm substituting for eta. So this becomes f naught over m omega n is k, and cosine 0 is 1, minus cosine omega n times t. Okay, this is the response. This is for all time. And here the response is obtained using the convolution integral. You can obtain the same solution. This is the same here. F naught over k1 minus cosine omega n t. Now let me talk about the response again, or how to obtain the response. For this problem, it is also convenient if using the convolution integral, or you can also use the equation of motion. Let me show you how to obtain this using the equation of motion. So alternatively, the problem for undamped is mx double dot plus kx equal to f naught. And initial conditions are 0. Then the solution of this differential equation consists of two parts. So x equal to homogeneous part plus the particular part. The homogeneous, you can refer to chapter 2. This will be a sine omega n t plus b cosine omega n t. And the particular solution is the solution that satisfies the right-hand side. That the left-hand side should satisfy the right-hand side. And since the right-hand side is constant, xp is also constant. So the only solution will be f naught over k. That will be xp, the particular solution. So as a steps to find xp, we look at the right-hand side. The right-hand side is constant, therefore xp should be also constant. And then you substitute in the differential equation, you will get m x double dot is 0, right? For a constant, plus k times c equal to f naught. And this will give you c equal to f naught over k. This is the total solution. And now you apply initial condition x at 0 is 0. Then this becomes b plus f naught over k, and this gives you b equal to minus f naught over k. And x dot at 0 is also 0. We get a omega n equal to 0, which means that a equal to 0. Substituting for a and b, we get x equal to minus f naught over k cosine omega n t plus f naught over k. We take f naught over k common. It is 1 minus cosine omega n t. So there are two approaches for finding the solution. We added to our knowledge now the principle of the convolution integral. Okay, this method you already know. Okay, this is the second method. It's called using the convolution integral. Convolution integral, as you can see now, maybe the convolution integral will involve doing integration, and you might think that this is will take time and it is more complicated than using this solution. Okay, but here for this type of the force, I agree with you that if you think this way, I will agree with you because the force is just a constant. But when the force is a pulse changing with time, it's given as a piecewise continuous. It's better to use the convolution integral. Okay, we will in the second section we will talk about some pulses, and you will see how we can use the convolution integral. Okay, now we obtain the response. What does the response mean? If you substitute for values for t, when t equal to 0, cosine 0 is 1. So this will start from 0. But you know that cosine varies from -1 to 1. So that's the only function of time. So if cosine equal to -1, we have 1 minus -1 becomes 2. So x also varies from 2 if not over k, sorry, from 0 to 2 if not over k. Okay, if not over k is called statical deflection. It's the same as delta, if not over k. So 2 times if not over k is twice, it's called twice statical deflection. This is undamped system, and the force is called step excitation. So step excitation mathematically looks simple, but its effect on the system is very severe. That it's producing twice the amplitude is twice the statical deflection. Okay, so you imagine that if you have let's say this is the spring mass system. Let me just make it longer. Spring. Okay, this is M and this is K. And this is the equilibrium position now. The effect of a step function, which means you are applying, suddenly you are applying a value of F naught. Okay, whatever that value is. This will take the mass to oscillate between this value and this. This is 2 times F naught over K. Okay, so if originally this was above here, this is F naught over K. This is before applying M, the mass. Okay, before applying the mass. But when you put the mass, it will go down to assuming this is, you know, F naught is equal to the mass. Okay, so this will make it as twice as delta. So it will oscillate from here. Okay, the result indicates that the peak response to the step excitation, this is the maximum value of the magnitude F naught is equal to twice the statical deflection, which is twice F naught over K. 2 times F naught over K. Okay, for zeta less than 1, which is the underdamped, this is h of t, and you can apply, which is e to the power minus zeta omega n t, okay, and we wrote it shorter, in a shorter form, e to the power minus zeta omega n t over m omega d sine omega dt. Okay, the equation, instead of using the convolution integral, he applied the differential equation, or he solved the differential equation. Okay, both methods are going to give you the same, of course, the same response as I showed you in the undamped system. Okay, so the final solution is x equal to homogeneous, which is x homogeneous plus x particular, the summation. And then you apply the initial conditions and you get the final response. This is the final response. And here is for different values of zeta. You can include with this graph zeta equal to 0. This will go up and down like this. This is for zeta equal to 0. Okay, and the effect of zeta, yeah, I will remove this, but I just give you an idea what will happen if you have zeta equal to 0. Okay, so if zeta is not 0, you can see that the maximum for the peak amplitude is less than twice f naught over k. Okay, so this is the ratio here given, x times k over f naught. Okay, so it is x divided by f naught over k, which is x over delta. And this is less than 2. If zeta is not 0, this is going to give you less than 2. The ratio will be less than 2. So as you increase zeta, this maximum amplitude or peak amplitude is, it drops. Okay, this is zeta 0.05, zeta 0.2, zeta 0.5. Okay, this is called the overshoot. Okay, and the oscillation will be about a new equilibrium line. Okay, it will not oscillate about the equilibrium line before applying F naught. Okay, so if the bearing mass system with damper, okay, this is the equilibrium position. The oscillation will be about a new equilibrium position when you apply F naught. It's going to oscillate about this. Okay, so it will take a new position now because of applying F naught. Okay, this is before applying, but once you apply F naught, this will be oscillating about the new equilibrium line. Okay, basic citation. Often the support of dynamical system is subjected to sudden movement specified by its displacement, velocity, or acceleration. That systems or structures, machines or structures can be subjected to ground motion that can be given as displacement or velocity or acceleration. Here we write the equation of motion in terms of the relative displacement. So originally, you can refer to chapter 3. We have that mx double dot equal to minus k times x minus y minus c times x dot minus y dot. And then you introduce z equal to x minus y, and you can write the differential equation in terms of z. Okay, and which is given as z double dot plus 2 zeta omega n z dot when you divide by m plus omega n squared z equal to minus y double dot. The convolution integral for system initially at rest will reduce to z equal to minus 1 over omega n integration from 0 to t of y double dot at eta sine omega nt. This is for undamped h of eta d eta. Okay, and there is a minus here because on the right hand side there is a minus, and there is no m here because it is not divided by m here. Okay, just to compare with the equation if it is in terms of x double dot. Okay, so the convolution integral for basic excitation will change to this equation for undamped, or you can use the for underdamped as well. Okay, now I'll move to pulse excitation and rise time, which is that when the system is subjected to a pulse that is changing, the pulse we have seen above was a step excitation, which is a constant, and that is the worst thing that the system will experience if it is suddenly applied. If suddenly force of a magnitude is exerted of a magnitude of f naught. Okay, so to have a more realistic applying force, there is a rise. This is called rise, and then becomes constant. Okay, so this will have less effect on the response than the step excitation, because the force is applied gradually. It depends on T1, of course, but it is applied gradually until it reaches F naught. Okay, so this is the same thing. This is a force, F of T. Okay, the same thing with if this is Y. You know, if you have a step and imagine that the car is going to driving over this road, and then it will have a step. Okay, let me just make the step smaller. Okay, so if the car comes, let's say that the wheel are, let's say, rigid, with a step, it's going to, you know, the wheel is going to have a step suddenly with no, there is no rise here. Suddenly it will jump. Okay, so this will give an excitation to the system with a sudden changes in the velocity, and will be severe vibration you can have if this is, you know, depends on the value of the step. Okay, so going gradually, this will have less effect on the response. Okay, it will be less than that of a sudden step. Okay, so there will be rise, and then this is a constant. Okay, I'm giving you this example because we feel this in while driving our, you know, cars. When we go over a hump or a step, we will feel the vibration. Okay, it depends on T1. There is more detail about T1 that is if T1 is greater than tau or T1 less than tau. Okay, this makes the difference. Okay, if T greater than tau, the vibration will be small as compared when T is less than tau. Okay, when T1 less than tau, this will produce something called shock vibration. Okay, because T1 is smaller than tau. Tau is the period of oscillation, the natural period of oscillation of the system. And T1 is less than tau. It means the changes of the step or the pulse is faster than, it's occurring faster than the response of the system. This produces shock vibration that will make the peak value very high. Okay, we will not talk about this because this requires more time. Okay, so we will study the response of an undamped system mainly. For one main reason, that if you are planning for designing any system, you will design it for the worst case. And this is the worst case. You have undamped system. Okay, as you can see from the previous section, that if you have damping, the overshoot will be less than the twice statical deflection, which is the case of undamped. So undamped is the worst case, that the system will experience, very high amplitude if it is undamped. So you can study the undamped system, and this will be also easily analyzed mathematically. So I'm not going to talk about pulse excitation and rise time for underdamped or damped cases. Okay, only for undamped system. Okay, there are different types of pulses. This is the first one is constant with rise. The second pulse is rectangular pulse, that is which is a constant and then zero. And then we have half sine pulse. Okay, and other pulses as well. Okay, so let's talk about rise time and then the constant. Already we talked about the constant before. Okay, from 0 to T1, to get the response here for rise time and the constant f of t is given as piecewise continuous. That is, the equation of a straight line is f naught over T1 times T for T less than or equal to T1 and equal to f naught for T greater than T1. This is called piecewise continuous. Okay, it is defined over intervals with continuous functions. The response will also have two equations, that x will be x1 for T less than or equal to T1 and will be equal to x2 for T greater than T1. Okay, so x also will be given as piecewise continuous. You can see that the effect of the constant is going to start after T1. So when you solve for the response from 0 to T1, you don't consider f naught, right? So you can use the principle of superposition and assume that this pulse, the rise and the constant, is equal to a rise with I will call it F1, which is equal to the equation of the straight line is the slope of naught over T1 times T. Okay, it is starting from 0, right? And then when T equal to 0, F1 is 0. And when T equal to T1, F1 equal to F0. Okay, this equation, of course, is valid. It can continue for T greater than T1, but you will not use it for T greater than T1. Okay, you will use it up to T equal to T1. But when you put this in the equation with the principle of superposition, you will use it with T greater than T1. So you have to cancel the effect of T greater than T1 that comes from F1. So what you will do, you will add another rise, but with negative slope, starting at T1. This is, I will call it F2. Okay, so what I'm doing is important because this will be what you will do. I have just 1 minute. And then I will stop. We'll come back to this next time. But let me just finish the idea, and then you can leave. Now F1 and what is F2 is using the principle of superposition that F1 plus F2. Okay, let's say for T greater than T1, F1 plus F2 should equal to F0. Okay, and from here you can find, excuse me for this color. Okay, F2 will equal to F0 minus F1. Okay, F0 as it is, F1 is F0 over T1 times T, substituting for F1. And this becomes, you can take minus F0 over T1, and this will be T minus T1. Okay, this is F2. Okay, this is the way to find F2. Okay, we will talk about this inshallah next time in more details, and how to find the response due to F1 and due to F2 and the total response for all time. Okay. Today, okay, for you, we have the lab on Thursday. Okay, so section 2 will have the lab today at 3. Any questions? Okay, مع السلامة.